Okay, how are you? Fine? Everything is going fine with the course? Okay, I put the video online just this morning because I had problems in the weekend and anyway, everything is online now and if you have any problem just let me know. So, I am moving forward with rainfall runoff modeling. I close the other door otherwise. And I'm not using for now the projector because I need the blackboard. But anyway, I am basically following the slides. And I just would like to remind you to put in a corner, and the corner would be here. The relationship that we determined to express the river flow according to the time area method, the integral relationship. So, if I remember the symbols, we wrote it in this way. Qt is equal to integral between 0 and t, the integral form, and I put, I think, as first term the derivative of the time area curve, the t, and then the precipitation in the tau. So can you please check if this was the relationship that I gave to you? Should be that. Just the symbology, I think, needs to be checked. It's okay? And I just would like to keep it here.
P is
rainfall. What did you use P or
E?
E.
I.
I tau, okay. That's it.
I T minus tau.
Okay, perfect. Yeah, that's correct. Of course. Minus tau in the tau, correct. Okay, let's keep it here, okay? And now, this was the rainfall runoff model that we studied so far, and we already developed an exercise on Friday to apply it to some rainfall data, and we just applied it. We didn't make a comparison so far between simulated and observed data. We just ran an application, and we will see later how to compare the simulation with the reality and how to adjust the time area relationship and the coefficient, the runoff coefficient C, to adapt the model to the observations, to maximize the fit of the model to the observations. I just would like to remind you that the rainfall that we are using here is already net rainfall. And the net rainfall is obtained by, according to this method, by multiplying the runoff coefficient C times the gross rainfall. Okay? So this is net rainfall. So you don't see the runoff coefficient here because it's already embedded in the value of I. But indeed, the runoff coefficient is one of the parameters of this model. Okay. Just a brief specification. What is a parameter? The models that we used, many of them contain parameters, and if they do, they are called parametric models. And a parameter, it's usually a constant, but could be also a variable. Usually it's a constant that dictates the specific form of the model, not the general form, but the specific form. Which means, like, let me provide an example, like linear regression, which is a well-known model that we use in statistics and other applications. The linear regression say that if you have a variable y that you would like to express as a function of an independent variable x, then you write y is equal to a times x plus b. This is the linear regression. And here in the linear regression, y is the dependent variable, in our case it's the river flow, x is the independent variable, in our case it's rainfall, and a and b are parameters. You see that these parameters do not change, they do not dictate the general form of this relationship. It's still a linear regression, no matter what the values of the a and b parameters are. It's a linear relationship for any value that you take for a and b. But the specific form of this straight line depends on a and b. So for instance, if here I make a picture, a graph of y versus x, I may obtain this curve, or this one. They are both linear relationship, but they are different. And they are different because of differences in A and B. So A and B, again, I gave again the definition for parameters. They dictate the specific form of the model, but not its general form, which is independent of the parameters. So, going back to our case, in our case the model is written there, it's the time area method. But the specific response of this model depends on its parameters, and in particular one parameter is C, the runoff coefficient. In fact, to apply this model, we had to fix a value for the runoff coefficient. On Friday, I gave to you the text of the exercise where a given value of the runoff coefficient was proposed. Okay. Now, let me introduce a second model, which is different with respect to the time area method, but there are some common features. And basically, in order to introduce the second model, let me remind you what was the schematization that was used to derive this model. This schematization was just a mass transfer of water from the watershed to the outlet. And we assume that this mass transfer takes place according to the position of the isochrones and according to a fixed velocity in time of the drops of water. So we assume that the isochrones are fixed in time, and then we assume that the response is just given by mass transfer. Okay. Now let me introduce a different model which is based on different assumptions. Still, our aim is to reproduce Qt, depending on what? On rainfall, of course. And let me identify with the variable IT, again, net rainfall. Let me introduce another variable, which is PT, which is the volume of rainfall per unit time. Which is equal to IT times A. A is the area of the catchment. So basically, you take IT, you multiply it by the area of the catchment, and what you obtain, even at IT, the dimension of IT is length over a time, because this is intensity of rainfall, if you multiply it by the area of the catchment, sorry, length over time was IT, not PT. If you take a length over time and you multiply it by the area of the catchment, here you obtain a volume over time. So it's the volume of rainfall per unit time. This is PT. Okay. The second model that I introduced is called the linear reservoir model. And it is based, first of all, on the application of the mass balance equation to the catchment. And this application is done by assuming that the catchment is like a tank, is like a reservoir. So basically, this is my catchment. This is my catchment, and I suppose that I get at each time step an input of volume of rainfall into this reservoir, into this tank. And I assume that there is a certain volume of water in the catchment, which I identify with the symbol W function of time. And then I assume that there is a discharge from the tank which is my QP. I schematize it as a bottom discharge. And then, if I conceptualize the catchment in this way, if I conceptualize the catchment as a tank, as a reservoir, I use tank and reservoir like synonyms, then I can write a mass balance equation very easily. I can write that PT minus QT is equal to the infinitesimal change of WT over time. This is, of course, straightforward. Remember that QT is a volume per unit time of water at the closure of the catchment, is a river flow, is a river discharge. PT is volume of rainfall for unit time. And here we have a volume over time, so the dimensionality is coherent. The dimensional analysis is coherent between the left-hand side and the right-hand side. Okay, that's fine. This is straightforward. But be careful. This is a mathematical equation which is physically based, where I introduced a state variable, which is the volume of water that is stored in the catchment. This is a state variable, which is unknown. It's not known. And therefore, in this equation, you have one known variable, which is rainfall, but two unknowns. So it's an equation that you can't solve by itself. You need to couple it with another equation. And what you should do is to introduce a second equation explaining WT. And so, if we think at the law of physics, can we identify a relationship that is able to provide us an estimate, a value for WT? Of course, if we refer to this scheme, ideal scheme of a tank, we know that there is a relationship in physics that can suffice to the purpose, can be useful for us. And what kind of equation could it be? Let's take into account that we already used mass balance equation here. So now the second type of equation that we could use is conservation of energy because I already mentioned to you that in fluid mechanics, conservation of energy and mass supply, and therefore a second equation would be conservation of energy. And indeed it's appropriate because here we have a flow that is originated by a tank, and the flow takes place because the potential energy of the water into the tank is converted into kinetic energy of the water flowing out of the tank. So we need an energy balance equation that is able to explain this transformation from potential to kinetic energy. And we know this kind of relationship from hydraulics. They are I don't know how to say in English because I think I have the term. And they are storage discharge relationships. And in Italian they are called leggi di flusso. But basically they are a relationship between the discharge from a tank and its storage. So they are a relationship between Q and W. And this is what we are looking for. So we need a storage-discharge relationship. And if we look at the theory of fluid mechanics, we have some physically based relationship for the storage-discharge. Some physically based relationship between Q and W. They have a problem for our purpose. They are not linear. So if you look at the law of physics, the relationship between Qt and Wt is non-linear. And this complicates our representation. So the idea of the people who devised this model was to approximate the relationship between Qt and Wt through a linear relationship. And basically, they adopted this relationship. Qt is equal to Wt divided by a constant k, which is a parameter. This was the idea. And as I said, be careful, this is not providing a physically based or a physically correct representation. This is an approximation of the physical law, which is introduced for the sake of simplicity. So we say that this model is not really physically based, it's conceptual. And it's conceptual for two reasons. First, for the approximation that I just introduced. Second, because the catchment is not like a tank. So there is a second approximation which is given by the fact that the catchment is not like a tank. But still, we have now two sets of equations which I can solve with the great advantage, as you will see, that the mathematical development is very easy, very simple, because I will obtain a linear model like the time area method. I already mentioned to you that this is a linear model, and this one also, as you will see, is linear. So this is a great advantage, especially if you put yourself in a condition that people who devised this model experienced it about 100 years ago. And the condition was that they had to make any computation by hand and not by using, they didn't have any computation facility like hand calculator not to speak of the personal computer. So of course they were looking for simple analytical relationship, simple analytical model, because they had to make any computation by hand. Good. Now, I told you that we can solve this model, so we can obtain an explicit relationship for Q, because this is what I'm looking for. I'm looking for a relationship that allows me to compute Q depending on rainfall, like that one. And therefore, let's see how we can derive an explicit relationship for Q, starting from these two equations, which we can call the constitutive equations of the model. Okay, so we have to integrate here. We have to perform an integral to obtain an explicit relationship for Q. We have to perform an integral. Why that? Because, you know, these are differential equations. So here you can see an explicit relationship for Q, but it depends on an infinitesimal change in water storage. And to describe this infinitesimal change in water storage, I have to solve this equation, and therefore I have to compute an integral. We will see how to do that. First of all, let's note that these two equations can be divided. It's quite easy. I can substitute the second equation in the first. And basically, here I have a W variable. Let me substitute the W value with the corresponding value that I can get from here. So these two can be combined to give PT minus QT is equal to K, or 1 over K, let me see, K dQ T in the T. Yes. Because you see that the dWt is given by K multiplied by Q. So here you see that I just substituted for dWt K multiplied by dQ. Be careful, when you combine two equations, so you start from a model representation that is given by two equations, and you combine them into one equation, this means that you are losing a variable. You see that now in this equation I have only one unknown. Of course, because if from two equations which correspond to two unknowns, you turn to one equation only, it means that you have one unknown only that is left. This is not a problem for us because the unknown that we eliminated is W, which we are not directly interested in. So it's not a problem. But of course, when you make such a combination in general, you have to be careful not to eliminate variables you are interested in. So if I had, for instance, eliminated Qt here, because I could do that, it wouldn't be a good choice, because I would eliminate the variable which I am interested in. In this case, it's fine, because I eliminated W, which I'm not directly interested in. Okay, now, let me take this equation, where you can easily see now that you have to perform an integral, because Q needs to be integrated here. This is an infinitesimal change of Q, so you have to integrate this equation. So let's integrate it. First of all, let's separate the variable, and let me write Pt is equal to Qt plus K dQt over dt. Yes. You have to always check what I'm doing. In fact, I forgot a K here. Okay. Now, let me multiply both sides of this equation for e to the power of t over k. So you see that I multiplied the left-hand side of the equation by this term, e to the power of t over k. And now I can say that this is identical to qt, which multiplies e to the power of t over k, plus k dqt in the t, which multiplies e to the power of t over k. Okay, perfect. Now let me rewrite the right-hand side, e to the power of t over k. This is just rewritten. And now let me bring your attention to the fact that the right-hand side is given by the summation of two terms, and I can express these two terms as the derivative over time of qt times e to the power of t over k, and this is multiplied by k. And now let's prove that this is true. I think it is straightforward, but let's prove that this is true. You know that the derivative of a product is given by the derivative of the first term of the product times the second term unchanged, plus the product of the first term unchanged times the derivative of the second term. So if I want to write this, if I want to explode this, I could write it as k, which multiplies derivative of the first between the t times the second term unchanged, e to the power of t over k, plus again k, which multiplies the first term unchanged, qt, times the derivative of the second, and the derivative of the second is a e to the power of t over k multiplied 1 over k, which is the derivative of the exponent of e, and this one disappear, and you get back the relationship that we started from. So we proved that indeed the right-hand side can be written as the derivative of qt times e to the power of t over k multiplied by k. Is this fine? Good. So I can read this last part where I proved that everything is correct so far. Okay, fine. Now, I can compute the integral for both sides of the equation. Why am I computing the integral? Because I need to compute qt, which is expressed here in differential form, and therefore I need to take the derivative of the right-hand side to express it in finite form. Okay, so let me say, and I change the sides of the equations because I want to put rainfall in the right-hand side. So I can write it this way. First of all, the integral of the second term. You see that the second term is a derivative. So the integral of a derivative is the argument of the derivative. And given that I compute the integral between 0, beginning of the event, and t, the current time, I can write the integral of the right-hand side in this way, k, which is unchanged, the argument of the derivative, qt, times e to the power of t over k, and this is computed between t and 0. And given that I introduced an integral, I have to define an integral variable. I have to substitute t with tau. So basically, again, I computed the integral on the right-hand side by simply taking the argument of the derivative, but of course I have to compute the argument of the derivative at the extremes of the integral range, which are 0 and t. And in order to be able to compute the argument of the derivative, the integral, for different values of t, I introduced the integral variable tau here. And this is equal to integral between 0 and t of p tau, integral variable, e to the power of tau over k in the tau. Perfect. Now we have to manipulate a bit things, and in particular we have to compute this left-hand term at the two extremes. So let's do that. But before doing that, let me, and allow me to make the change without rewriting. For simplicity, let me put k here, 1 over k, and delete it from here. Because k is constant, so I can bring it outside or inside the integral without any problem. Perfect. Now, let me write this by computing the q tau to the power of q tau times e to the power of t over k. Let me compute it for t and 0, so it becomes qt multiplied by e to the power of t over k minus q0, and that's it. That's it. Why? Because when I substitute at the exponent of e the value of 0 for tau, I get e to the power of 0, which is 1. So I just have, I get q0, and that's it, minus q0. If something is not clear, please let me know. Now we have to write the right-hand side, which is simply, I rewrite it, integral between 0 and t of 1 over k p tau e tau k in the tau. Now remember that our objective is to find an explicit relationship for qt. And therefore let's isolate in the left-hand side qt and just it. So let's write qt is equal to, and this is equal to q0, which multiplies e to the power of minus t over k because, you know, here I have qt multiplied by e to the power of t over k. If I want to get an explicit relationship for qt, I have to divide both terms by e to the power of t over k. So here I put the negative exponent, which means that I am dividing. Okay? Now I can write plus integral between 0 and t. Be careful, e to the power of minus t over k is a constant, because e is constant. We are computing the river flow to a given time t, which once defined is constant. So we can put this term, e to the power of minus t over k, inside the integral, because it's constant. So basically, I divide the integral by this term, and I can bring the term inside the integral because it's constant. So basically, I obtain 1 over k p tau e to the power of tau over k times e to the power of minus t over k in the tau. Okay? Now, of course, I can combine these two terms because they are the product of two powers with the same base e, so I can combine them. So let me write here qt is equal to the integral. I place the integral first, integral between 0 and t of 1 over k p tau